So I am in the molecular medicine pathway, and my mentor is Michelle Ferguson, and she's in the pediatric oncology department. And I'm looking at Langerhans cell histiocytosis, which I'm sure all of you have a very excellent working knowledge of. I'll probably give this talk before. So I just wanted to put this up there just to kind of let you know what I'm going to do for my whole year, but just know that this is, I'm not going to tell all of you about this today, because I really wanted to spend a lot of time on this talk at least, kind of laying the groundwork of what Langerhans cell histiocytosis is, why I think it's interesting, kind of what knowledge gaps there are and why, and kind of just give you a more clinical introduction of kind of where we're trying to go with this research project. And then maybe my second WIP, I'll just bore you with all of my new esoteric science details that I like. So this is kind of outline for today, so I think we'll just start with the history. So it's kind of an interesting history. It's kind of one disease, many presentations is kind of a thing that comes up with the disease. So this Hahn-Schuler-Christian disease, one of the first names that people assigned. Basically, this was back in the day when they didn't have any fancy stains or microscopy. So they were just looking at clinical pictures. And so these three different physicians were all writing about case series of pediatric patients who came in with this triad of exophthalmos and lytic bone lesions, usually in the skull, and as well as diabetes insipidus. And so that ended up in the late 1800s, they got this name of this disease. Elsewhere people were describing another disease, other different doctors talking about other kind of clinical pictures that they were like just grouping together for lack of a better place to put them. And this Lederer-Sue disease, I don't even know if that's how you pronounce that. This is pruritic rash, hepatosplenomegaly, and anemia, which is kind of this clinical picture that they recognized. Finally, we enter the age of radiology, and so people started noticing these rather strange bone lesions, usually solitary. They would put them in pathology and see just big granulomatous eosinophils, and so they gave it the very kind of boring name, eosinophilic granuloma, which is really, this is, I guess, the era of where you name stuff after yourself had ended. So finally, I think in 1940 is kind of when everyone started putting this together. It was actually Sidney Farber over in Boston, who at a conference, he basically put in evidence that all this stuff looks the same under the microscope. So maybe this is the same thing, just different presentations. It didn't really catch on for 10 years, and then finally they decided, okay, we'll name it this histiocytosis X, which maybe some of you have heard about, because that's still thrown around a bit today. Interestingly, the X is like, this is thought to emphasize necessity for the search for this etiologic agent. It's kind of an interesting historical aside. So then finally, flash forward a couple decades more, and now we have electron microscopy. And so electron microscopy is interesting because they first started looking at these LCH cells, Langerhans cells, and they noticed these guys, which are Burbank granules, which you also notice in Langerhans cells. So, flash forward and again another 10 years, and then they started doing immunohistocytochemistry staining on these guys, and they noticed that CD1A, again, is present in both the cells in this histiocytosis X, as well as Langerhans cells. And then finally in 1987, they renamed histiocytosis X to Langerhans cell histiocytosis, which is kind of the name that's still around today. Whether that will change in the future, it's possible. But that is
Dybbro's disease.
Yeah, hopefully. Bringing back that era of medicine. Speaking of great eras of medicine, so the Langerhans cell, discovered by Paul Langerhans, 1868 in Vienna, and he was a 21-year-old medical student. It was like you could look at things, if you built your microscope, you could name all sorts of things. So he, again, Langerhans cell, the pancreas, he also was looking at, ended up getting his name. He actually thought these were epithelial neurons because he saw the little dendritic extensions. We know now that these are just, these are not neuronal cells, these are dendritic cells, and they're present in the skin and in the mucosa. And then today, while the electron microscope and the Burbank granules are still technically the gold standard today, everyone just does staining. And so anything that stains CD1A and CD207 positive is considered a Langerhans cell epithelium. And I should also note that Langerhans cell histiocytosis cells also will be positive for CD1A and CD2. Okay, so back to now that we know that this is all like the same thing, like what can we say about this clinical presentation? So it really is a very kind of variable disease, both in presentation and course. Interestingly enough, you could see it almost any age. So you can see it in brand newborn babies, and you can see it in older adults as well. Again, the incident estimate is kind of, it's a rare disease. A lot of it is probably underdiagnosed, so it's a little unclear, but our best estimate is probably 2.5 to 5 cases per million. So it's not terribly rare, but it is still pretty rare. Again, so this is more common in children, and we tend to see more severe diseases in children, so it's considered a pediatric disease, but you do see it in adults as well. And again, like I can't stress enough this variable course. So I think in Fresno I saw 2 cases of histiocytosis randomly. One of them was just a newborn baby who resolved spontaneously, just some skin lesion. Another one was florid, hepatomegaly, and hepatic failure. So this is totally different people, same probably cell type, causing some entirely different cases. So clinically, the clinicians split it up into 2 big groups: single system, versus a multi-system. So the single system, if the what was previously termed eosinophilic granuloma, like just a little thing in the bone, we would call that single system. And it could be unifocal, so just one little thing in the bone, or multi, like maybe 5 or 6 little bone lesions. And this is in contrast to the multi-system, where you start seeing multiple systems involved. And I think the multi-system is probably the one that I find more interesting in that even within multi-system you can get high risk versus low risk disease, and depending on how much organ dysfunction you see. And most of the organs that are going to that bring kids into trouble, and we're talking liver, spleen, and as well as hematopoietic system, which causes a fair amount of morbidity and mortality in children. So again, clinical presentation is really going to be variable. It's going to depend on what flavor of disease the kid is coming in, or adult is coming in. That should specify. So again, it's like 50-50 almost, a little bit higher single system. Again, kids are going to be more often multi-system, so it's going to vary depending on age ranges. The CNS disease, it's pretty low prevalence, but it can be have a high morbidity rate, so it is something that is important that all clinicians are looking for in kids with LCH. Treatment, I don't even want to go into too much, but single systems tend to be more local based, and multi-system, of course, we're going to have to use systemic chemotherapy. In terms of survival, I think again we're looking at this is not current data, I should add. So I think our survival curves are going to be migrated upwards now, because this is 1954 to 1998. So our chemotherapy regimes have gotten a lot better. But I think the overall picture here is still pretty important. In like kids with liver, spleen, multi-system involvement are going to do much more poorly than kids up here who just think this is just bone. So in proxy for single system. Yeah.
Can I just ask, is this a disease of proliferative Langerhans cells or just atypical Langerhans cells?
Oh, we're getting there. Yeah, if I don't specifically answer your question, raise your hand, I'll make sure. But yes. Yeah, so this is from Northwest England, I should add as well. And this is just pediatric, so adults are going to look a little different as well. So I guess the big current controversies, I can't speak English today, in LCH that's still around today are, is this a neoplastic disease, or is this a disordered immune response to something unknown? And then another one that really has gotten a lot of traction is like, where is this LCH cell coming from? Is it really from Langerhans cell, or is it something from another type of cell type that is now having like an LC-like, a Langerhans cell-like presentation? And then of course, clinicians always are like, well, how do you explain this? What is different biologically between the kids who come in with high-risk multi-system versus low-risk multi-system, or multi versus single? So I think there's some newer evidence that's kind of piling on that looks like this is more and more of a neoplastic disease. A group, she's at Boston, I believe, used this kind of newer age sequencing, and they actually identified BRAF mutations. This is the B600E mutation in about 57% of cases that she looked at, and this is thought to be activating. We see this in melanoma, is kind of the big one that everyone thinks would be around. This is also seen in a wide range of other hematologic and solid tumors as well. Interesting enough, she didn't see any correlation with disease site or stage. Didn't really know how to explain that. She did say it looks like younger individuals were the ones that had this more frequently. And then when they did a little bit of staining looking at downstream of BRAF, and they saw all samples had some sort of upregulation of this pathway, but not all of them had this mutation. So something is causing this. But their end kind of gestalt of this paper was that this is evidence that this thing has a clonal mutation that is driving this, and thus we can consider this a malignant neoplasm. And then in terms of like where, yeah. So not yet, but they're Texas, MD Anderson, they're starting a clinical trial looking at BRAF inhibition because that it is probably a good idea. I think they're starting soon. Either they've just started or they're starting soon. In terms of where the cell coming from, another group looked at gene expression arrays, and they took LCH cells and they took normal LC cells from the epithelium. They saw a bunch of differently expressed genes, which is probably not too surprising. But when they looked at like what kind of signature is emerging from these LCH arrays, they found that it looks more closely related to a immature myeloid phenotype. And so what they propose is that the LCH pathogenic cell is emerging not necessarily from a mature LC cell. I apologize if the nomenclature is escaping me, but that is actually coming from somewhere higher up in kind of the developmental chain. I mean, the argument to this is that maybe this is just an EMT transformation epidermal to mesenchymal type, and this is mutating to look closer to a precursor cell. But I mean, this is what they're proposing, and I'll give you some more evidence that maybe at least in some cases, this might be important. So I think just to kind of summarize what we know, so this is a disorder. We see these LC-like cells. I'm being very plain and cautious here. Whether or not they're coming from there or not is another question. We do know it's clonal. There's a high frequency of BRAF mutations. So it's looking more and more like a neoplastic disease. But we still need a lot of work to say what's different between multi-system and single system, and how can we better target that for treatment. So again, I think this is just I just want to see this again just to stress this. So one of the first aim is going back to like where is the cell coming from, and then my biggest questions here is like, can we see evidence of an LCH cancer stem cell? And I'm proposing that we can, especially multi-system. And I just want to briefly talk about cancer stem cells because it's kind of I don't know if all of you have heard about them, but it's gaining a lot of traction actually in the field of oncology. 10 years ago, people thought you maybe were crazy, but this is now gaining quite a bit of traction. It was first, it kind of stems from regular stem cell biology, where we have like several progenitor cells that are capable of self-renewal, and then go on to produce all sorts of like differentiated and non-self-renewing progeny. So the cancer stem cell theory is that like say you have a normal stem cell, you get a round of mutation, and you get like a pre-malignant cancer stem cell that has the potential to become malignant, but isn't at this point in time. A few more additional rounds of mutation, and you get a self-selected malignant stem cell that's self-selected because it can propagate, it self-survives better. And that this malignant stem cell is now giving rise to a bunch of cancer cells that we see clinically. I don't know if I explained that well. So, I mean, this has gained a lot of traction because they've done a lot of genotyping of different types of cancers, and they've found that these are not necessarily genetically the same. They're very genetically heterogeneous, and so they're saying like different cancers may arise. They're arising from the same stem cell, but they're all each getting slightly different genotypic signatures. And so this is thought to be important because you give them chemotherapy and you kill off these guys, and if you leave some of these guys, you're going to get a recurrence, and these recurrences are going to be selected for chemotherapy. Yes?
Do they have any idea about, is it purely genetics that's driving that stem cell development, or is it environment, or do they know? Do they have any idea?
It's probably both. You know, stem cells are going to, like, the pre-malignant especially is going to be mostly environment. It's
That's
gonna
what I
be
was thinking, yeah.
doing its
but I
normal
just was-
thing.
Yeah, okay.
But by the time you get here, this is thought to be mostly driven by certain driver mutations, was what they would call it.
That makes sense.
Yeah. But of course, environment is important. So, interestingly enough, this theory is also in pediatric cancer as well. And especially in acute lymphoblastic leukemia, which is what is the most common pediatric cancer, a lot of people have hypothesized that these exist. They look at the fact that pediatric cancer versus like adult leukemias, just talking about leukemias, they develop over a relatively short interval of time. There's not a lot of environmental exposures to cause damage. Little kids don't have 50-pack year of smoking, etc. So several people have said, like, you know, this first mutational event must occur in utero because there's just not enough time to have a 5-year-old develop full-blown cancer, which is kind of a crazy theory. But these people said, you know what, if we look at children who go on to develop ALL and we go back to when they were first born or even in utero, they should have this pre-leukemic clone, which may not be malignant yet, but has some sort of genetic alteration that's priming it. So this is called backtracking. And so what these people did, they were looking at leukemia, and they looked at very specific TL-AML1 fusion, which is just a chromosomal alteration. They only looked at that because it's easy to PCR out. What they actually did was they looked at neonatal blood spots. So every newborn child in the United States of America gets a blood heel stick, and then they get collected on little cards, and they go off to they do all sorts of metabolic testing on them. But they always have leftovers, and so they are stored somewhere, and so you can get them. Quasi-ethical, whether you can use them, but these people use them, and I'm going to use them, so because you don't have to sign releases for them as of yet. But there are some legal issues pending with this. But anyways, their overall finding was that 2/3 of these cases that went on to develop this type of cancer had this rearrangement present at birth. So their end result was like this, whatever is going on happened in utero. So this is their kind of like overall just predisposed on the previous slide here. So like this is happening in utero, this is present at birth, and then this happens. And then this explains the fact you only have to go from here to here, explains why the time course is so less and you see 5-year-olds with full-blown yes?
Are they tracking this data spatially at all? In other words, across geographic range where these individuals are coming from?
Yeah, so only certain states will store the blood spots for extended periods of time. Does that make sense? So
Only certain states will store what?
we'll store these blood spots for extended periods of time. So I think California and Texas stores them indefinitely, and other states will do 6 years. I
guess my question is, do you have specifics on where the mothers are from?
no. This is just purely proof of concept at this point.
Okay.
I think there was some work done with that. I don't know the results, to be honest. Yes. So, you know, what do we have kind of like that goes with like this occurring in LCH? And I think, you know, we do see LCH fulminant disease in neonates. So something happened in utero, unless, you know, it happened as the baby was coming through the birth canal, which is probably what happened. Again, we see the more multi-system disease in younger children. Like, so could this be an explanation of why multi-system versus single system? Possibly. And then we also have like high concordance rates in monozygotic twins. So again, it's either genetic, something. But where does it arise is the question. So what I'm doing, kind of similar, I'm just, basically we are limited a little bit in that we only have paraffin blocks of this tumor, because it's pretty rare, most people just throw out paraffin. But we know that a lot of our tumors are going to have BRAF mutations, so I think that we're going to use that as a good starting point. We're going to screen all of our archived LCH disease tissue for this very classic mutation. And then we'll have to go back to blood spots, I can't speak. So this, this is going to be very different because we're looking for a single point mutation instead of like in that whole genetic fusion. So PCR is going to be not the way to go. So we're actually working closely with the guy who actually did the previous. He worked with the previous guy doing the backtracking. And we're actually going to be adapting this technique for our next generation sequencing, which is kind of exciting. And that way you don't just look for one single genetic mutation. You can screen for almost everything, and then even forward track if we want. But the goal, of course, would be like, can we see this mutation? Or if we discover more, can we go and see that whatever we find here, back here in these blocks? So I guess the other question is like, where is where is a cell from? Is this a mature LC cell down here, or is this one of its precursor cells, which are up here? And so, that paper with the microarray data set is probably up here. The question is it more of a myeloid precursor, or does it even go farther back? And so if you go far enough back, you start hitting all sorts of hematopoietic systems. So this is T cell down here, and then I think P cell further down. So interestingly enough, there's rare cases of this disease occurring in concurrence with a T cell leukemia. So this, I would argue, would maybe, if the same mutation is present here, is it driving the T cell leukemia down here at the same time as driving an LCH tumor down here? And so they've looked. These are pretty rare. So they've looked. The one person who first described it, at least biochemically or genetically, found these were clonally related, and he looked at TCR gamma receptor chain and found the same ones. And it's just an image. Like you should have a whole smear of them, and here you just have two simple spikes. He also found they've had the same mutation. And Notch1, I'm not going to go into too much detail, but this is very involved in hematopoiesis, so it's not necessarily something that's a shocker. So luckily for us, we have one of these samples. So we are collaborating with a person in Stanford who had this case as a patient. Ended up not doing well at all, actually. These patients tend not to do very well. But we have sampled both of the Langerhans cell as well as the T cell leukemia. So we're basically going to do the same things. Like, are they clonal? Is the first step, like in this case here. B, why not? Let's see. Do they have a Notch mutation? It's been described before. Can we see another one? And then, can we do the same thing with their blood spots? Because they were born in California, so there should be a blood spot. So that's kind of like the two big aims, I think. And I think I'm going to end it here, because I think next WIP is going to be very basic science. So, I just want to thank everybody. My PI, Michelle Harmerson. The St. Baldrick's Foundation funded me about 2 summers ago, so along my training, and then Prof Path is funding. It's an NIH, now defunct. Funding, so yeah, previous person. And then Weemels, Dr. Weemels is the guy who did backtracking. He's going to help us out this time around, and then Michael Jang of Stanford is the oncologist who did the 2 LCHs. So yeah, now take questions. Fast, but I have someone to be at 2:30. Yes.
Sorry, I just wanted to ask if you guys have an in vitro system to study.
So that's a very, very good question. So yes and no. So LCH to date has not been propagated in culture. There is a system that we're going to use as well.